Every time a charged particle accelerates, it sends a ripple of energy radiating out into the vacuum of space. This ripple is a dual structure built from two entirely distinct forces, an electric field and a magnetic field, locked together in perpetual motion. Looking at this 3D coordinate system, we can see exactly how these fields are arranged. The green and blue sine waves vibrate transversely, meaning they oscillate perpendicularly to each other. They also vibrate at a right angle to the actual path the wave is traveling. You can see the direction of propagation marked here along the x-axis, while the fields push outward on the y and z-axes. These equations describe that precise geometry mathematically. The electric field, E sub y, operates strictly on the y-axis, and the magnetic field, B sub z, operates on the z-axis. Both are defined by standard sine wave functions. The invisible communication network of the universe relies entirely on this highly specific, rigid 3D architecture of orthogonal fields. These notes detail a crucial rule of electromagnetic waves. There is a zero phase difference between the electric and magnetic fields. Physically, this means the two fields are perfectly synchronized. They both hit their maximum peaks simultaneously, and they cross the zero axis at the exact same fraction of a second. Vector math determines the wave's travel direction by calculating the cross product of the electric and magnetic vectors. Additionally, this boxed equation shows the ratio of the electric to the magnetic field is always a constant value. That constant is c, the speed of light in a vacuum. Because the speed of light is nearly 300 million meters per second, the electric field's numerical value is vastly larger than its magnetic counterpart. An electromagnetic wave operates within a strict proportional framework where electricity and magnetism move in perfect lockstep, driving each other forward at the absolute speed limit of the universe. The larger electric field produces perceived optical effects, identified as the light vector. Surprisingly, the total energy payload is split exactly equally between the electric and magnetic fields. We see this in their independent energy density equations, which use the constants of free space. Taking the ratio of these equations, we substitute the electric field E with CB. Expanding reveals the speed of light squared, defined as 1 over permeability times permittivity. This substitution cancels all variables, proving the ratio perfectly resolves to 1. This reveals instantaneous energy density at any specific microsecond. To find the average energy density over a full cycle, we use peak amplitude variables. Finally, multiplying this average density by the speed of light gives the wave's average intensity, or total brightness. The elegant symmetry of the wave ensures that its raw power can be accurately quantified, allowing us to predict the exact intensity of light hitting any given surface. With these rules established, we can analyze complex spatial data. If we are given a 3D mathematical formula for a wave, we can decode it to figure out its exact physical trajectory. This equation's spatial argument holds the wave vector data. Isolating the dot product yields the components 6j minus 8k. Applying sign conventions shows it propagates in the negative direction. Dividing this by its magnitude of 10 calculates the final precise unit vector path. These mathematical equations are precise coordinate maps, dictating the exact physical trajectory of energy as it navigates through three-dimensional space. When this perfect geometry of fields leaves the vacuum of space and enters a physical medium like glass or water, its behavior changes. The wave slows down. This reduction in speed, known as the refractive index, is calculated directly from the specific electrical permittivity and magnetic permeability of the new material. If a material alters those base magnetic and electric properties to specific new values, the math calculates exactly how much the light will bend, yielding a definitive refractive index. Carrying finite energy means the wave carries momentum. Striking an object exerts force, radiation pressure. Absorbing surfaces take all forward momentum, but hitting a reflecting surface causes a bounce back, requiring a double transfer of momentum, exerting twice the pressure. An isolated charge acceleratum in a vacuum instantly generates a rigid, self-sustaining 3D architecture. The oscillating geometry splits its energy perfectly in half, mapping out a precise trajectory as it travels. These fundamental properties explain how energy can traverse a vacuum for light years and still exert a measurable physical force on a distant object, a mechanism capable of pushing a solar sail across the galaxy using nothing but the geometry of light.